we are once again at the physics video lecture. Physics 107B video lecture 17. So we're in the middle of the potential formulation of electromagnetism. So let's write down what we had arrived at last time. We have, I'll just write potentials. So we have four equations, and start with the divergence of E. Actually, no, that's not where we're starting. We use those. So we're going to start with formulas for obtaining the electric and magnetic fields, namely the curl of the vector potential A, and E is minus the gradient of the potential, but it also had the time derivative of the vector potential minus dA dt. So the problem then turns into obtaining the vector potential and the scalar potential. And for those we have two equations. L squared V plus d over dt, divergence of A is equal to minus rho over epsilon naught. And then this one here, which has a wave equation look to it, L squared A minus u naught epsilon naught, second time derivative of A, minus gradient divergence of A plus mu naught epsilon naught d v dt equals minus mu naught current density. So those equations, should I number them? 1, 2, 3, and 4. So what we've gained here is, this is actually 3 plus 1 equals 4 equations, these two differential equations, from which we can obtain these 6 quantities by differentiation. Okay, so it turns into the problem of finding A and V. B, good. So next, how to obtain A and V from these differential equations. Well, we have a little bit more going on here. We have, in addition to these equations, we have the gauge conditions. So we have the gauge conditions. And that's what we ended with last time. And we'd even seen that it was very closely related to what we already have in mechanics. Okay, so the gauge conditions are that if we replace A by A prime equals A plus the gradient of the scalar, and if we replace V by V minus the time derivative of that same scalar, the equations here, or the fields, equations will remain unchanged such that the fields will remain unchanged. Okay, so that's the gauge freedom. Yes. So leaves the fields unchanged. And where did that come from? That came really from the fact that that B was curl of a vector potential, and relations with the scalar potential as well. So leaves the fields unchanged. Good, so that's what we have to work with. Now we're going to introduce two gauges. The first one really just for illustration, the second one's the one we'll work with for the rest of the time. So we have the Coulomb gauge. And that is to take the divergence of A vanishing, okay? So if the divergence of A vanishes, and we'll prove in a moment that that satisfies the gauge conditions well, but divergence of A vanishing, what that does is that simplifies this equation right here, okay? So the divergence of A vanishes, and we have now del squared V is equal to minus rho over epsilon naught. So that's a completely static problem, seemingly. There's actually a time dependence in here, but since these are just space derivatives, we can just integrate this up the way we've done before. And so we have V of R and T would be equal to 1 over 4 pi epsilon naught integral rho R prime and T volume element prime over R minus R prime. Okay. Integrate over all space. Yeah, that should do the trick, exactly. Okay, so that's what we have for our equation 3. The thing is, the E field is not yet obtainable from this, because we should, certainly we could have the minus the gradient of this V here, but we still would have to have the vector potential A in order to get the E field. So we're not even halfway to the problem. And I don't know if I'm going to write it out, but we would still have equation 4 to solve. Yeah, we may as well. So let's go ahead and del squared A minus mu naught epsilon naught d squared AT t squared. We'll just bring everything over to the other side that's left. We've got the minus mu naught J current density, and then plus gradient mu naught epsilon naught gradient dV dt. One thing you could do, you could declare this part solved, plug it in here, and then this is part of the given problem, and this is also given in your solving an inhomogeneous wave equation. Okay, so that's the Coulomb gauge. I'll just put that note that E still requires the vector potential to obtain. Good, Coulomb gauge. As far as the Coulomb gauge satisfying these gauge conditions, let's go ahead and do that as well. So what do we have there? We have divergence of A prime, so D, actually we'll even write the gradient here. We're going to write this thing out with the gradient as well. So gradient divergence, and we'll put the A prime in. So A plus grad lambda, and then we'll also take the plus u naught epsilon naught dv dt, which would be d v dt, and then minus u naught epsilon naught d dt of d lambda dt, so d squared lambda dt squared. So this thing here, we've already said divergence of A is going to be 0, so we end up with, right, this one goes away, we end up with grad, actually, okay, yeah, we end up with gradient, I'll go ahead and pull that out. We have del squared div grad, so del squared lambda and we have a minus u naught epsilon naught d squared lambda dt squared. Let that equal, and then I'll go ahead and say that equals gradient u naught epsilon naught dv dt. So here's the point. If this inhomogeneous, or if this wave equation is satisfied, and it can be satisfied in here, then we can see that as vanishing, and we're left with what we had before. Okay. We're left with just this term. Okay. So gauge condition is good, right? Extracting this wave equation is the key right there, because we'd be able to add the grad lambda to A. Right? Okay, good. So that's the Coulomb gauge. Let's look at the Lorentz gauge. In fact, I think I'll leave these equations up and erase this board. So the Lorentz gauge is a little more ambitious, because what we're going to do is require that this expression in parentheses vanish. Okay. So the Lorentz gauge and I just learned the other day that the T in here has been dropped and it's now a different Lorentz than it used to be. Okay, I don't know if that's fair, but the Lorentz gauge is going to be divergence of A is equal to minus u naught epsilon naught dv dt. Okay, so that's going to bring this entire expression to vanish, and let's see what we have now. So from equation 3, we have del squared v plus time derivative of divergence A. Okay, but the divergence A is this expression here, so the time derivative gives us a second derivative. You can see I can call this a minus u naught epsilon naught d squared v dt squared, and whatever I had on the right, minus rho over epsilon naught. Okay, so there we're looking at an inhomogeneous wave equation. And we see that we get the same thing in vector form for equation 4 here. Okay, this is going to vanish. We'll have del squared A minus u naught epsilon naught second time derivative is going to be equal to minus mu naught j. So that's really interesting. If we, we have the form now from well, if we drop the time-dependent terms here, we would actually just have the electro and magnetostatic expressions, and that's going to allow us to construct a generalization that takes care of these wave equations, okay, the time derivatives. Make sure I'm not missing anything before I get there. Yes, I'll just write gauge conditions question mark. Actually, you can tackle them the same way I just did the other ones. Should I write anything for that? It's also satisfied. Yeah, what we do is this thing here, what we do is go ahead and put in the divergence of A prime plus u naught epsilon naught ddt of V prime using these two again. And you can basically see what's happening again. You get that self-same wave equation because of these two. When you plug them in there, they just are declared zero again, like that, and then you get the resulting remaining wave equation. In the gradient, which means you can add that into A here. You can solve that wave equation. You got the whole thing. Good, so yeah, the gauge conditions are satisfied as well, etc., just like we did before. So now what we're going to do is first write down the static solutions, called the static solutions. And here we had, for this one we had V of R and T was 1 over 4 pi epsilon naught. The integral of the this is the one we just wrote down a minute ago, R minus R prime. Okay. So that was the, no T. Static solution. And the vector potential was the same thing here, different factors, mu naught over 4 pi, and then you had your J, and let's go ahead and write R prime. That's what we're integrating over, and there's our argument, J, R. And here we have the same thing. Oops, R prime, d tau prime, R minus R prime, A of R. So the generalization of these is found with the idea that the time dependence in both of these depends on the finite time it takes for a signal to go from R prime over which you're integrating to that point R, which is your argument. Okay, so there's a finite time involved, and let's and that finite time depends on the spatial relation right there. So let's clear some board and write that down. Okay. Oh, you know, I see I've missed something, the D'Alembert operator. I'll introduce that later. We actually don't need it right now. There's a D'Alembert operator. We'll do that later. So we want to solve these inhomogeneous equations. Okay. So let's just, actually I'll just write this down and then we'll discuss it. Source, right, charge or current. At R prime has an effect at R only after a finite time. It's just because of the speed of light. So we're going to say this distance that we're talking about, c times t prime, is equal to this r minus r prime. There's a distance traversed, and it took that this is equal to c times a certain amount of time. So because of that, we can define what's called, anything else to say about that? There was a lot, but we'll start with this, okay? You had a charge at one point, and the effect on it, you know, before when we were doing this, everything's instantaneous, right? There's no time dependence on in here. But now, if there's a piece of charge at R prime, those are primes, then it can only have an effect at R after a certain amount of time, okay? So what we're going to do is define the retarded time, delayed time, piece of R is t minus t prime. T minus that time it took to go there, which is piece of R is equal to t minus R minus R prime divided by c. Okay. Or you can use the that cursive R. You gotta be careful of the difference between the unit vector. So this R over C. Okay. So here's what we have. Now our charge density is rho of R prime, and then T minus is R over C. So when we take time derivatives, we're going to have to go to this, you know, spatial derivatives is the way it always was, but the time derivative is going to involve a spatial derivative as well via the chain rule in this argument here. So let's just go ahead and write down what those things look like. Okay, we're going to go into, this is how we're going to change these into time-dependent ones. We're just going to insert this expression up here and the same thing for J. Now, these equations have exactly the same form, so if we solve it for this first equation, we can just write down what it is for this one as well, okay? So what we're going to do is just write down what the solution is, and then we have to prove that it satisfies this differential equation. and V of R and T is equal to 1/4 pi epsilon naught integral. Now we have to have this rho R and T sub R d tau prime, so that's primed R minus R prime. This is it. This deserves a red box. So here's what our task is. We have to prove that this is a solution to this differential equation. And what's going to happen is the following. We're just going to do the del squared of V and show that it equals everything on the right side of that equation. So let me go ahead and write that down. So yeah, this is just a generalization of the static solution, and I didn't actually give that much of an argument for why it would be true. It really has to be demonstrated. This is just a fact about the propagation of electromagnetic influence, okay? But that this actually is our solution right there remains to be shown. It is required to be shown. Okay. So next, show that this del squared V is equal to U naught epsilon naught d squared V dt squared plus or minus rho over epsilon naught. And of course the rho is now this one right up here. Anything else before I do that? Okay, let's have a look. So the first thing to do is the gradient. So this is, so del squared is equal to, so del squared V is equal to divergence of the gradient V. And the gradient of V right here would be 1/4 pi epsilon naught, and then go into there. So we would have rho gradient 1/r minus r prime d tau prime. Oh, actually, put that outside. Plus 1/r minus r prime gradient rho. Yeah, just gradient rho. Now looking at those primes there, d tau prime. Remember, these derivatives are with respect to the r, not the r prime. Okay. So this here over 4 pi epsilon naught. The first one, rho, and then the gradient of 1/r minus r prime is -1/r minus r prime squared times r minus r prime vector over r minus r prime, because that's the gradient of the unit vector. Oh, that's the unit vector. Okay. And this other one is a little trickier. So here we have 1/r minus r prime gradient, that's why it's good to have this thing right out here. The gradient here is going to be d rho dt. Okay, so I'm doing with respect to this argument. I'm going to have a chain rule with a -1 over c, and then the gradient of that r minus r prime, which again is r minus r prime vector divided by r minus r prime magnitude. Close parentheses d tau. D tau prime volume element, okay. So it's actually best just to focus on this for a moment. The next thing we're going to do is divergence. So next, divergence of gradient V. And I'll just recall or note that the divergence of a scalar times a vector is equal to the vector dotted into the gradient of the scalar plus the scalar times the divergence of the vector. And so we need these product rules because this is what we're looking at right here. Okay. But we should be able to see what happens. So there's a product rule right here. One of these, since we have this here, I'll put the vector rho like that, okay. So this is just minus vector over vector cubed, basically, okay. And that means when you do the divergence, when you do the scalar times the divergence of this thing here, you're going to get just the 4 pi delta function. Okay, 4 pi times the delta function of r prime. There's a prime right there for the first part of your product rule. The second part, it's going to be the vector here dotted into this gradient of rho, which is something we just did up here, right? Gradient of rho. Oh, yeah, put the d rho dt in this. And this will just be vector dotted into a unit vector, so I'm just going to turn this into a magnitude. With the d rho dt, we're just going to cancel the one when we do the product rule here, and then the other product rule that doesn't get canceled is going to be bring out the second derivative of rho here, d squared rho dt squared. So that's why I'm just going to write down the answer. So we're going to have, well, not quite the answer, 1 over 4 pi epsilon naught integral. Let's see how I've written it. I'm using these cursive R's here, or am I not? So we're going to have I'll do them in this order. So from over here we have a 1 over c squared we have a 1 over c squared. We have 1 over c, we get a second one, 1 over c squared d squared rho dt squared. And I don't have the right power here. Squared. I think this is the power of my notes. I don't have that. The other one is minus 4 pi rho d cubed r minus r prime. close parentheses d tau prime. Okay. 4 pi r squared. Should cancel that. Yeah, this must have been the correct power. Okay. So here's what we're going to get. Oh, no. It's a little fast. This was the right power. 1 over r minus r prime. Magnitude. Okay, good. Here's what's going to happen. Time dependence from this one gets pulled out, and we're left with 1 over c squared d squared rho dt squared d squared dt squared of 1 over 4 pi epsilon naught integral rho r minus r prime d tau prime. Fantastic. Okay. That's 1 over c squared d squared v dt squared. Okay. And this one here, we integrate the delta function at r prime, we're just going to get 4 pi rho. Of r, because we're integrating over r prime. So 4 pi rho of r. Yes. And that's going to cancel the 1 over 4 pi, so that's going to give us the rho over epsilon naught. Good. Okay, so now we do have it. We have well, I didn't actually complete my, here we go. Del squared v equals, here, down here. Okay, once more we'll go. Del squared v equals this right there. So good, we can box that in up here. So we have found, did I announce it here somewhere? Yeah, we've actually found this. Del squared v, we've got the 1 over c squared d squared v dt squared, because that is the v. And then the delta function integrated up, we got the rho over epsilon naught. And I did a little hand waving on this, but you can see where each of these expressions comes from. You get a cancellation of the two, the time derivative one here and the time derivative here times the space derivative there. And then you're left with the second one, second time derivative. So this went over to here, and this one left over there. Okay, good, and that is what we set out to show, so that now we know that this is the potential with the retarded potential is what it's called, and then we also have the same thing for A. So, and A of R and T is equal to U naught over 4 pi integral J of R prime T sub R d tau prime R minus R prime. And always good to have this expression there in front of you when you're going to take your derivatives so you don't get mixed up. There was a space derivative with respect to that. But since we were integrating over the primes, we never did a space derivative with respect to r prime. Okay. Good, let me consult the time here. Yeah, I think that's a good place to leave it. So we now have these results. These are our potentials, right? This works. And I think what we'll do next time after the break is first just do some examples, visualizing what's actually going on here in some concrete cases. Okay? But formally we have the solutions. They're a really natural generalization of electrostatics and magnetostatics. With this retarded time expression. Okay, good. See you guys next time.